Assalamualaikum and a very good day to our panel, Dr. Nur Syahidah binti Sabri and Dr. Muhammad Syafiee bin Mahmud. Let me introduce myself first. My name is Nurul Nabiha binti Muhammad Syahid and my supervisor is Dr. Hatini binti Ahmad Rafai. Today, I would like to present my research regarding on photodegradation of methyl orange dye on titanium dioxide doped zinc oxide nanocomposite photocatalyst under UV irradiation. Now, let's move to the introduction. So, water pollution has become a dreadful scenario due to continuing propagation of industrialization and lack of stringent quality control policies against the discharge of dye pollutant in wastewater bodies. Synthetic organic dyes such as methyl orange extensively used in the textile, paper, plastic, leather, food and other allied industries. Influents containing other dyes that are discharged into lakes, rivers become toxic and cause severe environmental problems. So, photocatalytic degradation by using semiconductor metal oxide is the best solution for water treatment. Titanium dioxide and zinc oxide are promising semiconductor that can be used as a photocatalyst to remove the organic pollutant and contaminants. And then the photocatalytic oxidation is considered as a low-cost and eco-friendly method. Despite the potential advantages of zinc oxide, the photocatalytic activities of zinc oxide are limited by the irradiation wavelength in the UV region due to the wide band gap. And then the absorption ability of the high energy portion UV is restricted. And then the last one, the fast recombination of the electron hole pair, which decrease the photocatalytic degradation efficiency. Therefore, the objective of the research is to synthesize the titanium dioxide doped zinc oxide nanocomposite at different weight ratio as a photocatalyst by ultrasonic assisted chemical mixing method, and to investigate the structural and optical properties of titanium dioxide doped zinc oxide nanocomposite, and to examine the photocatalytic performance of titanium dioxide doped zinc oxide nanocomposite photocatalyst under UV light irradiation. In this research, it is related to three main processes, which is the photocatalyst, photocatalytic degradation and doping process. So what is photocatalyst? According to the Belfer 2019, photocatalysts are materials that decompose harmful substance in the presence of UV rays from the sun. This technology is based on the use of a semiconductor that can be excited by light with an energy greater than its band gap, causing the formation of energy-rich electron hole pairs that can be involved in redox reaction. And then the photocatalytic degradation is an environmentally friendly technique that has emerged as a promising alternative for the degradation of a wide range of organic pollutants. It is a process where the organic contaminant in water will be degraded by using the UV light. UV photooxidation functions as an eliminator, removing organic compounds via ultraviolet radiation, and then photolytically activated certain metals that will then act as a catalyst, according to the Alexia. And then a new approach to achieving more efficient charge separation has been provided by the coupling of two semiconductors, as it gives some benefits such as follow, which is the increased lifetime of charge carrier and enhance the interfacial charge transfer to absorbed substrate. Next, the main material used in this research is zinc oxide. According to McLean 2019, zinc oxide is the nanoparticles constitute one of the most studied semiconductor oxide and widely applied materials due to its remarkable photocatalytic properties such as eco-friendly, cheap, and non-hazardous. It is a representative N-type semiconductor with a broad direct band gap of 3.37 electron volt and has a high excitation binding energy of 60 mega electron volt. Zinc oxide drawbacks including fast recombination rate of the photo-generated electron hole pairs, which disrupts the reaction process and limits the effective degradation of pollutant by this photocatalyst. Next is the titanium dioxide. Titanium dioxide is the nanoparticle is considered as an appealing nanomaterial due to its versatility. It is a low-cost, non-toxic nature and relatively high photocatalytic activity in ultraviolet light, according to Oladipo 2019. It also have a high sustainable efficiency due to their chemical and physical stability, large surface area, corrosion resistant, and biologically benign. The titanium dioxide requires a band gap energy of about 3.2 electron volt, thus making it primarily active for UV light. Titanium dioxide only relies on UV light, which only makes up to 3 to 5% of solar radiation due to fast charge recombination in titanium dioxide-based material. The last one is methyl orange. Methyl orange has frequently been used as a model dye to investigate the photodegradation chemistry that occurs on semiconductor particles. Metal orange is a widely used and well-known azo and ionic dye, and it contains aromatic and double bond and group in their molecules, which are highly toxic, carcinogenic, and teratogenic, and are harmful to the environment and organism, according to Wu 2021. The absorption spectrum of the metal orange solution will be investigated around the wavelength of 466 nanometer. Therefore, in this study, we will be undertaken to find out the efficacy of doping semiconductor-based catalysts, specifically titanium dioxide, doped zinc oxide. Next, we move to the next chapter, which is the methodology. This is the flow of preparing the sample by chemical mixing method. In this slide, shows the simple flow the evaluation of photocatalytic activity. A 5 mg per liter of metal orange was dissolved in 1000 ml of DI water. Then the zinc oxide and titanium dioxide doped zinc oxide with various weight of titanium dioxide were dissolved into 100 of metal orange solution. The solution were exposed under UV light irradiation for 1 hour. 5 ml aliquots of the solution will be collected every 10 minutes for progress in photocatalytic degradation by measuring the absorbance using UV visible spectrophotometer at 466 nanometer. The following is the method used for the characterization of sample, which is by using the UV visible, FTIR, photoluminescence spectroscopy, EDX, and last but not least is SEM. Next, we move to the chapter 4, which is the result and discussion. In this slide, exhibit the SEM image and morphology analysis of undoped titanium dioxide, zinc oxide, and different weight of titanium dioxide, doped zinc oxide nanocomposite at a magnification of 1000 and 5000 respectively. Undoped zinc oxide and titanium dioxide doped zinc oxide samples are evenly distributed and well dispersed. Based on the observation, all prepared samples were found agglomerate, and the particles represent a similar structure. Further characterization on the elemental composition of titanium dioxide doped zinc oxide was conducted using EDS chemical mapping analysis. The EDS analysis confirmed the presence of 3 elements, which is oxygen, titanium, and zinc in the titanium dioxide doped zinc oxide sample. The distribution of these 3 elements are consistent with the distribution of titanium dioxide doped zinc oxide particle. It shows that the presence of these 3 elements with no other impurities peak detected in the EDS spectra, confirming the purity of the sample. Elements zinc, oxygen, and titanium show a complete coverage of the image frame, and titanium element was scattered homogeneously on zinc structure. The titanium weight percent from EDX shows that the amount of titanium in the sample increased with increasing dopant concentration during synthesis at 3.45%, 9.41%, and 11.40% for 5, 10, and 15 weight percentage of titanium respectively. Next is the FTIR analysis. In this slide, it shows the FTIR spectra for each of the sample. From this graph, it revealed the multiple peaks related to titanium dioxide without any other elemental contamination. According to the previous study, in the range of 865 to 470 area, the FTIR spectrum of titanium dioxide exhibit a broad band assigned to titanium bond oxygen bond titanium and titanium bond oxygen vibration mode. The intense peak near of 554.34 is correspond to the titanium bond oxygen stretching. The strong absorption peaks obtained between the 430 and 540 is attributed to the stretching mode of zinc bond oxygen. The peak observed at the 676.35 may be associated with the vibration of the titanium bond oxygen. The other peak at 1735.72 and 1736.32 may correspond to the carboxylate, which is C double bond oxygen stretching. For more detail, we can refer from this table where it shows the functional group for each peak from this FTIR spectra. This graph shows the photoluminescence spectra of titanium dioxide doped zinc nanoparticles. The UV emission is observed around the 380 nanometer, originated from acetonic recombination in the near band edge of zinc oxide. It would observe that the photoluminescent intensity decreased as the titanium dioxide content increased from 0 to 15 weight percentage. The maximum photoluminescent intensity for 5% titanium dioxide dopant is attributed to an increase in free carrier concentration. The electronic transition from the titanium dioxide shallow donor level to the oxygen vacancy deep acceptor level become another mechanism responsible for luminescence, as titanium dioxide is incorporated into zinc oxide nanoparticles. As a result, the visible photoluminescence intensity is enhanced. However, further titanium dioxide content in zinc oxide nanoparticle reduce the visible photoluminescence. That is for the UV-vis analysis. From the graph, it can be seen that the characteristic absorption intensity of methyl orange dye at wavelength 466 nanometer for each sample slightly decreased after 60 minutes. Based on the graph, photocatalyst comprising 500 of titanium dioxide doped zinc oxide perform the highest photocatalytic activity with the efficiency of 28.25% under 60-minute irradiation time, while the other titanium dioxide doped zinc oxide samples show a percentage degradation of 21.68% and 6.67%, and for 10% and 50% titanium dioxide doped zinc oxide respectively. When the doping of titanium dioxide exceeds higher than 5 weight percentage, it can be seen a decreasing pattern in the photocatalytic activities. Previous studies have been reported that higher content of titanium dioxide dispersion could have a negative impact on wastewater treatment because the particles can block the UV light path, resulting in a reduction in degradation efficiency. In conclusion, the titanium dioxide doped zinc oxide nanoparticles were successfully synthesized using the ultrasonic assisted biochemical mixing method. The highest value obtained for the percentage degradation photocatalyst of methyl orange under UV light irradiation is 5% titanium dioxide doped zinc oxide, which is 28.25%, and the rate constant is 0.3319 per minute under 60-minute irradiation compared to other photocatalysts. Longer irradiation time is expected to degrade the methyl orange dye molecule, while excess amount of titanium dioxide could show that the UV light absorption resulted in the reduced photodegradation efficiency. Photodegradation is influenced by several basic parameters, including substrate concentration, photocatalyst amount, pH of the solution, reaction medium temperature, and light irradiation time. Therefore, for future work or for a recommendation for future researcher, this parameter could be investigated for better result in this research study. So that's all from me. Thank you.